Okay, thanks everyone. So this talk will be about benchmarking and general performance metrics in Kotlin, but not only in Kotlin, also in Java. So first of all, my name is Artur Dziedziczak. Originally, I'm from Poland. I love programming, and in ING, I work with Java, Kotlin, and some DevOps. I'm a member of Nakamoto Savings team. Before I go further, I want to ask who of you ever did some benchmarking in Java or Kotlin, micro benchmarking? Hands up. Okay, and who heard benchmarking or read about it but never actually tried? Okay, cool. So this talk is mostly for you. So people with entry level of benchmarking knowledge and people who want to see the examples of benchmarks in real Kotlin code. So the agenda is following. First, I will discuss what are the benchmarks, define them. Then I will discuss how to find performance issues with Kotlin code and JVM. Then I will show some opinions on micro benchmarks, facts on micro benchmarks, show some demo code, and well, the naive demo code that you can also write, and mostly this is how you benchmark your code. And later I will show you how to do it properly. So first of all, when you search what is a benchmark, there are many different types of it, but for the sake of this presentation, I decided to divide it into three. We have these meso benchmarks, which test only certain features of the application and the flow of it. Macro benchmark is the one that tests whole application. And there is also micro benchmark, which usually should test this one small functionality and checks how fast does it run. When it comes to finding those performance issues, because before you even start thinking about benchmarking anything, you need to be critical and start thinking, okay, how do I even know that the application that I wrote is slow in some parts? How to find those issues? First of all, you need to measure. If you don't measure how your application behaves with different tools like profilers that are presented there below, or IDE profilers, you won't know if there is a performance issue. So first of all, measure it. Before me, someone mentioned the open telemetry. I think this is also a really good way how you can be sure that there are no performance issues, or if there are some, you can find them. With logs, you can also be sure that something is going wrong with your app. But most importantly, be critical about it. We write different code. Everyone can make mistakes. Something can go slow. And yeah, be critical about thinking about metrics. In the end, you found this one. You found this performance issue in your application. You detected that probably it's one function or one set of functions bundled into one feature. You put some favorites show on one screen. On the other one, you open your code editor and start writing benchmarks. And you should not do that. All the people on the internet says that it's just a waste of time. And it presents not only bad, but sometimes fictional results. I will show you how such results look like. But in general, people are really critical about it. And it's not only a matter of opinion, but it's a fact. Actually, for JVM-based languages, micro-benchmarking can be a huge waste of time. But it's not only opinion, as I mentioned, it's a fact. So what are the arguments of the people who say that micro-benchmarking is something that you should not do? Well, first of all, when you micro-benchmark this one function of code, what can happen is that the compiler will completely differently compile this one particular code than the whole application, which for sure will happen if you have larger code base. Next, your final code probably runs on some high-end machines, and those high-end machines are completely different than your MacBook, even if it's virtualized environment. Probably it can have even different set of instructions that when you actually run it, then yeah, it can be much, much faster, and this benchmark can give you wrong results. The access of the memory for real application is much more probable that it will have some cache misses, not only when it accesses the memory, but also when it accesses the CPU cache, depending on what actually hardware you use to run your code. So this can happen, and a lot more actually. So in JVM, you have a garbage collection. There are different languages that have also some kind of garbage collection. It is invoked in many different ways. But in real-world application, probably you will find that there is an issue with that. And your benchmark, even though I will show you ways how you can prevent it from happening, still it can. When you did not start to find the function that actually causes issue with some profiler or with some metrics, you can really start to micro-benchmark wrong pieces of code. So you need to be aware that the micro-benchmarking starts only when you're really certain that this particular piece of code is the one that can cause problems. Lastly, this micro-benchmarking in Kotlin and Java is like asking ChatGPT to multiply fractional numbers. It will give you results, but probably wrong, and you won't be aware of that. Now I think it's a bit fixed, but yeah, I mean, if it's plain a large language model, it won't. With all of that, you might wonder why I'm even making presentation about micro-benchmark if it's so bad. Well, there are some cases where I think personally micro-benchmark has some advantages. So first of all, when you find this one function in your code base that needs to have, when you find this one function that has performance issues and you would like to improve it, measure if the code that you actually start rewriting has a better performance. Next, if you have some range of metrics that you would like to ensure in your CI that this function will always run within a certain metric. Even if your colleagues deploy some changes that you don't want, with this you can ensure that it will still be there. Lastly, you can also make sure that the performance of this function is good before the deployment. And I can imagine that if you have like some trading application written in Java that you need to have a lot of really tightly scheduled invocation of function, this can really make a difference. If your colleague changes something, you will also know that it was changed. So to conclude, writing those micro-benchmark with all we know is like cycling through Amsterdam at 5 p.m., close to Central Station during King's Day. So yeah, it's really hard. I don't know if you tried it, but it is. Let's do it still. I mean, yeah, that's why I did this presentation. Before that still, some definitions. JVM in general needs some warm-up phase to actually make sure the code you run, it is like warm-up for the actual benchmark. So whenever you create benchmark, even by your own, you need to make some iterations before you even start calculating the results. Next is the set of iterations. Let's call it iterations. And this is the number that will actually, how many times your function is invoked. And this is the part that you actually measure. Other than that, there are different benchmark modes. So there are many different libraries that can do that, but in general, you should focus on throughput and average time. If we define this throughput, is the number of function calls per unit of time, and average time is average time which takes to execute this function. There are others, though. The Kotlin X benchmark library that I use actually has those, but there are others, just for you to be aware on that. Okay, now some naive example of how probably most of you measure how performant is your code. So to do that, I will do it like this. Are you able to see the screen? Cool. So this is a benchmark that I found on Oracle website. It was written in Java, just to give you an idea how you probably also do it. So you probably skip this one. You don't have any warm-up phase before you actually start computing the results of how fast your function runs. And then inside some loop, you perform computation and check throughput with the average. In my case, I'm benchmarking micro-benchmarking 3 functions. The distance, it computes distance between 2 points. Crazy compute, which does some crazy math calculations, and also based on this distance, and constant that doesn't do anything. This constant is actually super important, because if you don't use the constant benchmark, you don't even know if the function is properly not optimized. Now, if I go to the application, how to invoke this, you basically started with the parameters, you have some runnable code, and what is interesting here is that you need to either do something with this variable, like here last, you can print line it, or return it. If you don't do it, it will be probably completely optimized, and the result will be that all of the functions will have the same invocation time. Okay, now let's go to the results from this. If I run it, we can see that the throughput of this benchmark, we have crazy compute, which has pretty low throughput. Not many operations within period of time are performed. Then we have constant, which actually has the highest one. Makes sense, right? Because it doesn't do anything, so it can do it as fast as it can. And distance is lower. This is the naive example, and it has almost all the issues that I mentioned before. So it can be optimized, and in general, depending on where you invoke it, the whole metrics can be different. There is a better way for that. And the better way is basically to use this Java micro-benchmark harness. The definition of it is that it is a harness for building and running, analyzing nano, micro, milli, macro benchmarks written in Java and other languages that target JVM, like Kotlin, which is good. We don't have to re-implement that. I use the Kotlin X benchmark library, and I must say it's still pretty hard, because even though it takes a lot from you, like you don't need to make those loops. The warm-up phases are also defined there. It doesn't take the thinking part from you. So you still need to be aware that many, many things can go wrong, even though the tools are prepared there. Let's write the proper benchmark with this Kotlin X benchmark. It's much simpler if we go here to bad benchmark, because it's still bad. You can see that there are many annotations on the class. First of all, you define the time unit which you're interested in. Then how many of the warm-up phases you need, and the measurement, how it will be taken. Also, it is important that you need to specify the mode. As I mentioned before, I will only work with 2. So one is the throughput, and the second one is average. Then you have the setup of the benchmark that will be invoked before each of the benchmarks, and some black hole that will consume the result. You can also just return a result from this function, and it will give you some metrics for that. There is an issue here with this code. I don't know if you notice what can be wrong, because it seems like it's right. Come on, we have arguments, we have some black hole that will consume results. Well, it is not. So as you can see, the distance benchmark is totally optimized, and it is optimized during the runtime of the application. Crazy benchmark, even though it has those parameters that are the same, seems not to be optimized. So, wow, it's super weird. Even though I thought I did something right, like everything right, it is still not giving me proper result. Constant should not be the same as distance. Distance is actually computing something. The results come from 2 different machines, so you can also compare how good Apple M1 is in comparison to my good old Dell. But yeah, in general, there is an issue with that. So if we go to how to make it better and properly, we go to good benchmark. And this good benchmark is actually really good, because it also randomizes the input for the methods that will be invoked. If we have this in place, we can see that, oh, okay, it actually starts to be more convincing for us. First of all, the constant benchmark has a really nice throughput, and then distance is computing something, so we know that, okay, it's actually probably also right. We have the baseline, and the crazy benchmark also should be lower than the distance, because it computes more. When it comes to other modes that you can use, because this one gives you operations per second, right? You can see that it's actually quite a lot. There is also a way to take the average. I don't know if you noticed the change here, but we moved now from milliseconds into nanoseconds. This is important, keep that in mind. So if we go to the average, and average time of how long does it take for the function to be finished, if we go to the benchmark, the only difference is actually this part where you define that now you're not interested in throughput of how many invocations of those functions can be invoked within some period of time, but you only care about what is the how long does it take to compute this one particular function. As you can see, I also changed the benchmark time unit to nanoseconds, because millisecond, as I will show you in a minute, it's not enough. It won't give you proper results. So here we can see that constant benchmark takes like 6 nanoseconds, and distance benchmark gives you a bit more than 8 on my dial. When it comes to M1, this is much faster, right? It's like 2.5 nanoseconds. What is also interesting, the difference is not that big anymore between the constant benchmark and the distance benchmark. So maybe it's possible that this M1 has actually a better set of instructions to do all of that instead of my old Dell. This is what I also mentioned before. So like, if you think about micro-benchmarking, I run this in 2 different machines. How can you even take numbers from micro-benchmark if on 2 different machines, the output is completely different? I mean, the ratios might still be there, but come on, it is different. It can go even weirder. So I run this benchmark on my good old Dell, and it comes up that crazy benchmark lasts like 200 nanoseconds, and this is completely different than the average benchmark of Apple M1. If we go to the charts, it's actually a crazy difference, because there are like 200 times more. And I was digging, okay, what can go wrong with that? And apparently there is a reason for all this computation. If we go to the benchmark itself, at the very bottom, we will see that for iteration number 2, 3, and 4, my laptop decided that it won't compute that fast, and apparently it took much longer. Taking average from those iterations gave result, which meant like, okay, is M1 super like SpaceX technology that it's so fast? No, apparently not. It's just the iterations that were slow. What I would need to do, again, is to run this benchmark or just look at the numbers and not at the average result. It's not really something you think about when you micro benchmark, right? Because you should just take average and forget about what else it outputs. Here, no, sadly, you still need to do it. So yeah, keep that in mind. Things that need to be done right when you do those micro benchmarks. So first of all, you always need to create the baseline for it. If you don't have the baseline, as I showed you before, you're not even sure if the benchmark that you wrote is giving you proper result. And I think this is the crucial part. Remember that if you want to remember one thing from the talk, just get this baseline right. Next, the constants and local variables that are present in your code, and especially in the benchmark code, will probably get optimized. So try to not use them, or if you can, because I can imagine for some functions you cannot, try to always randomize this input. If you randomize it, it's less probable that it will give you the results which are not true. And as you've seen, it's actually hard to detect if they are not true, especially if you don't make this baseline right. I also mentioned in the beginning of this presentation that there is a warm-up phase. So actually, it's quite important. And now I will show you how this JVM is actually warming up to perform your computation. Here you can see that the throughput is growing And it is growing quite drastically, I would say. When the iteration happens, there is like, I don't know, 40,000 operations per second more than when you actually start computing the average of the numbers. Then it's like this, not only for this particular case, but in general, those numbers make a difference. So here you can see that it's also for this good benchmark, distance benchmark. The amount of operations grow with the time the benchmark is performed. If you skip this warm-up phase, it is possible that you will completely miss this. So don't skip it, and it's super important. Now a bit of math. So average Spring Boot response, let's say it's 50 milliseconds for, I don't know, returning string. Then average call of this crazy compute is like 200 nanoseconds. If you convert it to milliseconds, this is the result, okay? So 1 nanosecond is equal to 1 billionth of a second. To give you some like feedback how much it is, it's actually 9 zeros. So I don't think optimization for such numbers can make sense. And if you ask yourself, should you micro-benchmark your code? I would say, I don't know, maybe you should, maybe you shouldn't. It all depends on what are your requirements and what do you want to achieve. People say on the internet that you should not, but I think for some particular cases, this can be really worth it. For JVM, sadly, it's super hard to do it, but if you use C++ or any other language that compiles directly to the hardware, then it gets much easier. Sadly, here with all those optimizations, it can be pretty tricky. If you do it, just remember to always measure. If you don't measure how this benchmark performs with the baseline, it can give you completely wrong results. Compare it with baseline, so also you're sure that actually the measurements make sense, and be critical about it. If I go back to this previous slide where this happened, if I would not go back to this particular log, I would probably say you that, yeah, the M1 is so much faster, you know. But I went back, to like my critical thinking, and started to ask questions. Why crazy benchmark is so much slower on this other machine? Yeah, when it comes to the presentation itself, it's all. I wanted to show a huge pride flag because it's June, and that's it for the presentation. I hope you liked it.
Thanks a lot, Artur. I think one can definitely tell that you were very passionate about micro-benchmarking, and
yeah.
was a very funny presentation, nice analogy with riding a bike through Amsterdam on King's Day at 5 p.m.
Happened many times, yeah.
Are there any questions from the audience? Yeah.
Yeah, I'm not so experienced with micro-benchmarking, but I'm wondering, have you ever tried to solve all these JVM issues which you mentioned with a warm-up and different architecture where application can be run? Can you try to solve it maybe with running Java application compiled with a native?
I haven't tried it, but this Kotlin X benchmark supports that. So I think you can use GraalVM and do it. But also keep in mind that if you move the running code from one hardware to another, the issue will actually still be there, you know? So I can imagine that if you use those high-end Dell server machines and you don't deploy with Docker, the issue can be, like the difference can be really drastic there. So yeah, I think there is no solution, but just try to be critical about it and do it properly.
I have a question that kind of connects to that. One of the things that can give trouble is garbage collection. It's possibly one of the issues you showed. do you know of any strategies to maybe invalidate your results when garbage collection occurs during your measurements?
I think if we go back here to this part, I'm not really sure what happened here for this crazy benchmark. Maybe it was also a garbage collection. I'm not sure. The thing is, you really need to go to the end result log and decide from the numbers, like critically decide if it was right. So it all, as I mentioned also here, it takes a lot from you, but in the end, it doesn't take the thinking part. You need to do it yourself. There is no other way.
Are there any other questions? I think yeah.
Thank you for sharing information for nice feature of Kotlin code. Can it be applicable for Salesforce application development? Can Kotlin code enhance Apex functions in Salesforce application?
You ask about the performance of it?
Sorry?
You ask about performance of Kotlin, because to be fair, when you
about performance in Salesforce or other CRM databases.
Well, I don't think you can actually micro-benchmark connection to database. This would not make sense because the latency of it will be so much higher than actual micro-benchmarking that I do. So for that, no. But I think if you parse the response from the database, for that, I think you can micro-benchmark it, especially if you loop through some collection. With this, you can play around, make a benchmark for it, and get results which will show you that you did it good or bad. Yeah, but the Salesforce, to be fair, I don't know.
Salesforce is written in Apex. It's also language close to Java. Mm-hmm. But now I see that some Kotlin's features are better adapted to Salesforce, for some Salesforce application.
Oh, okay. So if it's JVM based, I think you can use this Java micro-benchmark harness, and if it provides you API or some kind of SDK that you can also use micro-benchmark straight from this. But you need to have a code that will be prepared for it.
Okay.